We're starting the more the classic type of physics, chapters 2 through 7. And we're going to do 2, 3, and 4 before we have a big test. I might have some quizzes involved, and I'll have some homework, but we won't have a test for more than a week. All right, so you're okay on that. Well, here's this word, and I didn't know this. Even when I was in college, I'd never heard the word mechanics used except for people who fix cars and engines and things like that. Have you heard that? I'm a mechanic, you know. And yet in physics, mechanics has to do with the study of motion. So anything that moves would be in the category of mechanics. If you went to college and you became a physics major, first of all, you should like math really well. You should like computers really well. And you should like physics. If you like physics, math, and computers, you might really like physics as a major. You get that? And some physics people get into astronomy. Some physics people just get into theoretical physics. But if you're studying mechanics in college, it would be probably calculus-based study of motion. I'm not going to be using calculus here. I might use a little bit of algebra, maybe a little bit of trigonometry, a little bit, but not very much. You get that? So mechanics is the study of motion. And so what I want to do here is we're going to start at this chapter, and I'm just going to lead you into this chapter a little bit. And so well, I'm going to go ahead, I'm going to read this whole page to you, and then I'll have somebody else read. I just want to get a good start today, all right? And then I'll ask you some questions about what you think we read. All right, let me start. It's good when your personal life is stable, when things important to you are in balance. And it's also nice when the needs of the family and friends are in harmony. Financially, we prefer our expenses to be balanced by earnings. Economists are concerned with the balances between inflow and outflow of goods. These examples illustrate the idea of equilibrium. In nature, we see an energy equilibrium when energy radiated away from the Earth is balanced by the input of solar energy from the sun. Whenever a glass thermometer acquires the same temperature as the object being measured, we have thermal equilibrium. There are many forms of equilibrium. In this chapter, we will be concerned with mechanical equilibrium. Things in mechanical equilibrium are stable without changes of motion. The rocks shown to the right are in mechanical equilibrium. An unbalanced external force would be needed to change their resting state. So we're getting ready to enter a really neat part of physics, a big part of physics called mechanics. And some of the stuff I'm going to read here, you already know. You get that? That's the good news. And some of you don't know. So somebody want to read right here? Just read through here. Yeah, go ahead. Thank you. Can you close the door for me, Ian? Go ahead.
A force is a push or pull. A force of some kind is always required to change the state of motion of an object. The state of motion may be one of rest or of moving uniformly along a straight line path. For example, a hockey puck at rest on ice remains at rest until a force is exerted on it. Once moving, a hockey puck sliding along the ice will continue sliding until a force slows down. A force is needed to change an object's state of motion.
Go ahead and start right here, net force.
Net force most often more than one force acts on an object. The combination of all forces acting on an object is called the net force. The net force on an object changes in motion. For example, suppose you pull horizontally on an object with a force of 10 pounds. If a friend assists you and also pulls in the same direction with a force of 5 pounds, then the net force is the sum of these forces of 15 pounds. The object moves as if it were pulled with a single 15-pound force. However, if your friend pulls with a force of 5 pounds in the opposite direction, then net force is the difference of these forces, or 5 pounds per pound. Resulting motion of the object is the same as if it were pulled with a single 5-pound force. This is shown in figure 2.1, where instead of pounds, the scientific unit of force is used, the Newton, abbreviated N.
Okay, one more paragraph.
When the girl holds...
When you hold. Oh, this one. When you hold a rock.
Can you scoot it up?
Oh, I'm sorry. All right.
When you hold a rock at rest in your hand, you're pushing upward on it. With as much force as Earth's gravity pulls down on it. If you push harder, it will move upward. If you push with less force, it will move downward. But just holding it at rest, as shown in figure 2.2, means the upward and downward forces on it add to zero. Net force on a rock is zero.
Okay. So some of this you already know. We know that there's this world called the scalar world. The scalar world are measured numbers that direction doesn't matter. 3 grams. Do I need to say 3 grams west? Direction makes no difference there, right? If you're measuring 5 centimeters, it's not 5 centimeters north. Those are all called scalar quantities, and most of your life, you only deal with scalar quantities. You get that? And so you like the scalar world. In the scalar world, what is 5 plus 3? What is 5 grams plus 3 grams? It's always 8. That's why you like the scalar world. But when you get into the vector world, the vector world says the measured, what you're measuring in this vector quantity has magnitude and direction. Now 5 is a greater magnitude than 3. That's easy. But then direction matters just as much. And so here, what is a 5 Newton force to the right plus a 10 Newton force to the right? You say, well, that's not 15 Newtons, it's 15 Newtons to the right. Forces must be a vector quantity because direction matters. Now what about here? A 10 Newton to the right and a 5 Newton to the left. When they're going in opposite directions, you subtract and you give it the direction of the greater magnitude. And what about 5 left and 5 right? Then the net force is 0. So this is going to set you up for the next 7 chapters. So everybody got that? Is that pretty simple? Yeah. Now, so vector quantities, direction matters. And we did this before. I even had a test question on there that said, what is 5 plus 3 in the scalar world? It's always 8. What is 5 plus 3 in the vector world? Well, the biggest number could be what? 8 in that direction. And the smallest number could be, now we did this before, 2 in the direction of the 5, isn't it? But what else could it be? What if I don't do this? What if I go like this or like that? Then it can be any number between 8 and 2. It could be 3.555. It could be any number between 2 and 8. Now, we had talked about that before when we did the big 6. I'm just kind of reminding you of that because the vector world, you have to tell me the magnitude and the direction in the world of forces. Now, here's something that we'll find out in another chapter. And this is Newton's first law, which Galileo pretty much came up with it, but Newton says, let me tell you, I think I have 3 laws that govern most of what you see in the universe. And the first law has to do with something that Galileo kind of figured out. And even though they're 100 years apart. It says, have you ever heard this? An object at rest tends to what? They even have a commercial now. They're trying to push pharmaceuticals. And it's about a person that says, you better take our medicine because if not, you sit in that rocket chair too long, what are you going to do? An object at rest tends to what? Stay at rest. Is that what you want to do? They're trying to scare people. Take our medicine. Then you'll be up and moving around, see? And they're trying to use Newton's law, one of Newton's laws of motion, to sell pharmaceuticals. Okay, that's good marketing. I remember it. An object at rest tends to what? Stay at rest. Now, wait a minute. An object in motion tends to stay in motion, listen, at a constant speed in a straight line, unless acted on by a set of unbalanced forces, or a net force, you might say, okay? Now, I need you to remember that because a lot of what we're going to see in the next 6 or 7 chapters has to do with that. And it has to do with this funny-looking thing called sigma F equals 0. And what does sigma mean in math? You ever use sigma in any of your math classes? It means the sum of. Oh, you knew that already? I'm sorry, you knew that? If the sum of all the forces equals 0, then two things are happening. This is important because you're not going to think about one of them. If this is true, if the sum of all the forces, also known as the net force, isn't it?
Yeah.
If the net force, or the sum of all the forces equals 0, then there are two things that I know about that object. One, it's either at rest, it's not moving, or two, it's moving at a constant speed in a straight line. Now, here's what I have to do, and here's what I love about conceptual physics. Your mind will be altered in the next few chapters. What you thought was common sense, you'll say, that doesn't make sense anymore. When I see a car go down the road and I'm talking to the person on the phone, tell me exactly how fast you're going. 30 miles an hour, 30, 30, 30, 30. Are you going in a straight line? Yes. What can I tell you about that car? The net force on that car is 0. And you say, no, the person's foot is on the gas pedal. I know that the engine is hooked onto the transmission. I know the transmission is trying to push the wheels. There's no way the net force is 0. The car is being pushed down the road. I agree. The car is being pushed down the road. But I also know that the net force in that car has to be 0. If you see any object at rest, or you see any object moving at a constant speed, you tell yourself the net force is 0. You don't like it that there is a force going that way, pushing a car that way, but there's another one pushing a car backwards. And it's equal in magnitude, and it's opposite in direction. Now, you can call that air resistance or drag or whatever you want to call it. It is equal. The force driving a car that way is equal to the force pushing the car that way. How do I know that? Because the net force in our car has to be 0 because of this thing called inertia. Now, I need you to think that way. If you look at this table and it's not going anywhere, the net force on that table is 0. Did I say there were no forces on that table? I never said that. I know the earth is pulling that table down. I know it is. Well, then why isn't the table going down? And you start saying, I never thought like this. Something must be pushing the table up. And what is that?
Floor.
The floor. And it doesn't, maybe it doesn't sound right to you. And you said, no, I don't want you to change. I don't want you to change the way I think. Well, really? No, because you're telling me something I don't like. Okay. And for a long, long time, people didn't understand this at all. Aristotle, you probably heard him, right? He was pretty smart. He wrote things about everything. He wrote things about animals and plants and medicines and pain and everything. And what happened is, so many of his things were based on what people saw, what you might call common sense, that it was adopted as truth. It was truth. Everything he said was true for like 1,500 years. Even the church, I think, made a bad mistake by thinking, this is so true. I know it's not biblical, but it's so true. We're going to bring it in to the church and say, that's as true as the Bible. If you say something about the earth and that Aristotle didn't say, then that's blasphemy. Nothing in the Bible talks about this necessarily, and yet that was a mistake they made. And so for 1,500 years, nobody, you got in trouble if you told them something like, I think the earth sits still. Everybody said yes. That's what Aristotle said. Aristotle would have said that the sun and the stars go around the earth. We're sitting still, and they're going around us. And that made everybody happy for a long, long time. And then some people got some evidence that said, something that doesn't seem right. I don't think the earth is sitting still. Blasphemy. And again, they shouldn't have linked that kind of truth with biblical truth, but they did. And so for a long time, nobody knew this stuff that I'm telling you right here. So it's okay that you're a little uncomfortable saying, you mean with a jet plane with all those jet engines, and it's going at 1,000 miles an hour and 1,000. You're telling me the net force in that plane is zero?
Yes.
That's right.
Oh, okay.
Now, I will tell you, I never said that the net force in that plane was always zero. That plane had to get up to 1,000 miles an hour, didn't it?
Yeah.
And we'll find out later that you cannot change your speed without a net force. And that's what this says. If I have a constant speed, I will not change that speed unless a net force is put on me. Now, if I'm in a car going 30, and all of a sudden I put on the brakes, and he says drops down to 25, 20, 15, there was a net force in what direction? Backwards.
Yeah.
And that's why you slowed down. If somebody were to push on the gas pedal and went from 30 to 40, the reason they went from 30 to 40, they changed their speed, didn't they?
Yeah.
There must have been a net force. There was. The force going this way for a while was greater than the force going this way, and that's why he would speed up. So this is one of the basis of the next few chapters, okay? All right, do you have any questions on this page? All right, let's take a look at the next page. Now, again, you already know this. You already know this. It says, this is called a spring scale. Everybody see that? And it's about, what's that say? 9 newtons? Is that what it says? Okay. Or actually, okay, let's go 10. Let's pretend that the spring scale says 10 newtons. Now, this box is not going anywhere, is it? So what's the net force on an object that's in mechanical equilibrium? What's the net force? 0. But how can it be when the Earth is pulling down with 10 newtons? Right. Let's see this. Whether it's my finger or whether you attach it to the ceiling, there has to be an upward force of what? 10 newtons. One of the books that Paul Hewitt wrote, I don't think he has it this year, but one of the chapters, they always have like a picture and chapter, the beginning of the chapter. And they had a little boy, probably about 8 years old, and he's on a rope, it's going like this, like that. And it says, oh, you've played tug of war before, haven't you? Which one's greater? The pull of the boy going this way or the pull of the other boy going that way? And you can see he's not going anywhere. Which one's greater, this pull or that pull? They're the same. And then, but the best part of that chapter, or that picture, says, what if the rope was not attached to another boy, but attached to a tree? Now which one's greater?
That's a little bigger.
Whoa, I never thought about that.
The same.
Yeah, it is.
Oh.
But it's not a person. It's not a person choosing to pull. But when I pull on that tree and I'm not going anywhere, the pull on the tree that way equals a pull here. What's interesting is, what if the boy decides to pull harder on the rope? The tree will pull back harder. You don't like that either. You don't like that this table, for example, see this table? Watch. I'll push down on it a little bit. What's the table doing?
Pushing back.
A little bit. Now, I'm going to push on the table hard.
Oh.
And my hand didn't go anywhere, did it? The table is pushing back harder. This table has many ways it can push back. Many. Now, if I made this table out of paper, it would not have the properties of being able to push back. And so if I made it out of paper, it couldn't push back enough, and my hand would go right through it. But a lot of these materials, they can push back. Here's another one I'm going to do for you. Take your finger like this and say, I want you to make the last digit of the finger bend upwards, and probably your skin will change colors.
The interruption. We have a couple of athletic announcements that I need to get out. Varsity tennis tryouts will be canceled today. They will be moved to Thursday. And varsity soccer, you have been moved to the gym. Thank you.
Okay. Yeah, girls soccer. Is that what they meant? Okay, now watch this. make the last digit of your finger bend upwards, and your skin will probably change color. Right? Do it.
Oh, we're starting our finger.
You say, oh. Now, do it with a little bit of help.
Break your finger.
Oh, I did it. Now, you say to yourself, well, of course, because what makes my finger bend and change colors? A force going this way, right? And you said, and as a matter of fact, I knew that. I could feel that I was doing it. Now watch. Here, say with me. Now do this on the table. Oh! What's the table doing? It is pushing back.
You know how like you poke your finger through the water bottle packets? They kind of bend your fingers.
Okay, now we could talk about this all day about what kind of things you can push your finger through, what can you not, and some of those items you can push it through, and it'll keep pushing back until you reach its limit, and then your finger will go through it. But it can actually push with quite a bit of force, but it can break. You can exceed the limit of it's able to be a push. So I need your mind to think a little differently because you love the scalar world, and I need you to kind of think in the vector world. All right, let's take a look down here, and I need somebody to read these two paragraphs right here, all right? Can everybody read it from that? Can you see it well enough? Can you see it well enough?
Should we turn down the lights?
Anybody? All right. Anybody have a book? You want a book? Can you read it for me? The next two paragraphs, please. Tension and weight,
If you tie a string around a 2-pound bag,
Hang on.
If you tie a string around a 2-pound bag of sugar and suspend it from a scale, a spring in the scale stretches until the scale reads 2 pounds, as shown in figure 2.3. The stretched spring is under a stretching force called tension. A scale in science lab is likely collaborated to read this 2-pound force as 9 newtons. Both pounds and newtons are units of weight, which in turn are units of force. The bag of sugar is attracted to the earth with a gravitational force of 2 pounds, or equivalently 9 newtons. Suspended twice as much sugar from the scale, the reading will be 18 newtons. There are two forces acting on the bag of sugar: tension force acting upwards and weight acting downwards. The two forces on the bag are equal and opposite, and they cancel to 0. The net force on the bag is 0, and it will remain at rest.
How do I know that the sum of all the forces on that bag are 0? How do I know that? What?
It's constant? Or it's not moving?
It's at rest, isn't it?
Yeah.
And even if it was moving, it could be moving at a constant speed in a straight line and still have a net force of 0, couldn't it?
Yeah.
So I need you to think about that all the time. Anytime you see an object it's at rest, the net force on an object is 0. If you see an object, any object that moves at a constant speed, the net force on an object is 0, whether you like it or not, and whether you understand it until maybe tomorrow you will. All right, then what they do is they go into the idea of what's a vector and what's a scalar. And I want to pause just a little bit. Yes, this will take me about 5 minutes, but I'm going to read this to you. I happen to know a little bit more about this author than you do. Paul Hewitt got a degree, and then he went out. And he couldn't quite find a job back then. He was actually an artist, and he got a job, and that's when they actually painted billboards. Billboards for a long, long time were painted. They didn't have machines that could make these great big sheets that people glue up there. You see that? Now we have electronic billboards, but at one time you painted them. And so he happened to work with this guy named Burl. And Burl didn't even graduate from high school, I don't think. But it changed Paul Hewitt's life. He said every time they worked together, this guy, he loved to ask questions. Hey, Hewitt, why is the sky blue? Hey, Hewitt, why don't the clouds fall down? How come they don't just fall down? Hey, Hewitt, what about this? Hey, Hewitt. And he always questions. And here Paul Hewitt says, I went to school, and I even took physics, and I couldn't answer his question. And so when he started this about 40 years ago, he went back and he said he was going to make a new kind of physics book. And the physics book was conceptual physics, where you thought about the concepts. And yes, you might do some math, But I linked with this, I connected so well with this because when I took physics, I didn't necessarily like it because I liked math and I was just taking another math class. Every day in physics, here are the formulas, plug in the numbers, use your calculator, and find the answers. What did I know? I knew how to plug and chug. He even has parts in the book. It's called plug and chug. Meaning, yeah, part of that is physics. You have to use the equations, plug numbers in, and solve for something. And that's like math, isn't it?
Yeah.
So I agreed with him so much that I knew a lot of math, and I could plug and chug, but I couldn't answer a lot of questions conceptually. You know those 3 chapters he had on water, liquids, solids, and gases? I knew none of that. I knew none. I couldn't really explain Archimedes' principle to you. I'd never known the concept behind it. And the same thing here. So if you don't mind, give me about 3 minutes or so. I'm going to read this little story about Paul Hewitt and Burrell. Is that okay? All right. So let me enlarge it just a little bit more so in case you want to read along with me. When I was in high school, my counselor advised me not to enroll in science and math class, but instead focus on what seemed to be my gift for art. I took this advice. I was then interested in drawing comic strips and in boxing, neither of which earned me much success. After a stint in the U.S. Army, I tried my luck at sign painting, and the cold Boston winters drove me south to Miami, Florida. There, at age 26, I got a job painting billboards and met a new friend, Burl Gray, a sign painter with an active intellect. Hey, Walker, put your head up, please. Burl, like me, had never studied physics in high school, but he was passionate about science in general. He shared that passion with me by asking many fascinating science questions as we painted together. I remember Burl asked me questions about the tension in the ropes that held up the scaffold that we stood on. The scaffold is simply a heavy horizontal plank suspended by a pair of ropes each end. Burl twanged the rope nearest his end of the scaffold and asked me to do the same with mine. He was comparing the tensions in the 2 ropes to determine which was greater. Burl was heavier than I was, and he guessed that the tension in his rope would be greater. Like a more tightly stretched guitar string, the rope with the greater tension twangs at a higher pitch. That Burl's rope had a higher pitch seemed reasonable because his rope supported more of the load. Are you with me so far? So here's this person. They never really took physics. I made a mistake. Neither one of them took physics in high school. Burl and I exaggerated, and that's what physics people do all the time. If you want to answer a physics question sometimes, what you do is exaggerate the situation. You get that? He said, Burl and I used exaggeration to bolster our reasoning, just as physics people do. If we both stood at the extreme end of the scaffold, and they have another picture where they both move there, then it says, and we leaned outwards, it was easy to imagine that the opposite end of the staging rising like the end of a seesaw, with the opposite rope going limp. There would be no tension in that rope, and we reasoned that my rope, and here's what they do over here. See how they got on both sides here? Then we reasoned, there you go, and gradually decrease as I walked toward Burl. It was fun posing such questions and seeing if we could answer them. See, right now, all of the tension is in this rope here. You see that? All of it. Like this rope is limp. See that? So the weight of this plank and the weight of them and their paint cans, why aren't they going anywhere? Why aren't any of these things going anywhere? Everybody should know. I've already said it 3 times today. They're in mechanical equilibrium, right? The sum of all the forces had to be 0, right? And so here's all the weight of the plank, the weight of them, and that's going down. Why aren't they going down? That rope must be pulling up equal to all of this, because there's no tension here. You get that? And then they ask the question, all right, what happened when I was coming towards you? When we were over here, you're heavier than me, and so a little bit more force is in, more tension there than here, but what happens as I walk towards you? And that's what they ask. That's what a physics person would do. What happens if I walk towards you? What happens to the tension on this? What do you think? If you start going, twang, all right, we go twang, 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 and I start moving towards you, what's going to happen?
Pitch goes up.
Twang, 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 twang. And what about this one? It would go down. It said here, a question that we couldn't answer was whether or not the decrease of tension in my rope when I walked away, would it be exactly compensated for by a tension increase in Burrow's rope? For example, if the tension in my own rope underwent a decrease of 50 newtons, would Burrow's rope gain 50 newtons of tension? We talked pounds back then, but we use the scientific unit of force now, newtons, today. Would that gain be exactly 50 newtons? And if so, would this be a grand coincidence? I didn't know the answer until more than a year later when Burrow's stimulation resulted in my leaving full-time painting and going to college, to learn more about science. At college, I learned that any object at rest, such as sign painting scaffolds that support us, experiences no net force. That is said, it's in equilibrium. That is, the forces that act upon them, the sum of all the forces is zero. So the sum of the upward forces supplied by the supporting ropes do indeed add up to the downward forces of our weight plus the weight of the scaffold. A 50 Newton loss in one would be accompanied by a 50 Newton gain in the other. And the last paragraph, here we go. I tell this story to make the point that one's thinking is very different when there's a rule to guide it. Now when I look at any motionless object, I know immediately that all the forces on it cancel out. We view nature differently when we know its rules. It makes nature seem simpler and easier to understand. Without the rules of physics, we tend to be superstitious or see magic when there is none. Quite wonderfully, everything is beautiful, connected to everything else by a surprisingly small number of rules. The rules of nature are what we study in physics. And that's kind of interesting. Again, I know that that's a little bit of his editorializing and part of his life, though. All right, let's go over here. And let's take a look at this drawing right here. Consider the gymnast above hanging from the rings. If she hangs her weight evenly divided between the two rings, how would scale readings in both supporting ropes compare with her weight? What if she hangs with slightly more of her weight supported by the left ring? So let's pretend that we have spring scales right here. And spring scales can measure forces, okay? In this case, tension forces. Let's give her a weight. What weight would you like to give her? Let's make an easy number. How about 200 newtons? Is that okay? Let's say that she weighs 200 newtons. That means that the earth is pulling down with 200 newtons. Well, why isn't she going down? Why is she not going down? Jeff. Hey, Jeff. Put your head up, please.
I can't see those eyes.
All right, ready? Why is she not going down? The earth is pulling down with 200 newtons. So why isn't she going down?
Because the earth pushes back with 200 newtons.
Why would if that's the case, we would not have to spend a lot of money with fuel getting rockets off the earth.
Wait, is saying why is she not going down?
Yeah.
Because there's more force going
No,
on.
it's not more.
Okay, now if there was more force going up than going down, I'd see her moving up. Matter of fact,
Well then it's equilibrium then,
okay, how do you know it's equilibrium?
because she's staying in the same spot.
That's right. Now, this is called static. Static equilibrium is talking about an object at rest, and later you'll get one that has to do with moving, equilibrium when you're moving, okay? But now, here's what my next question is. How much tension is in that rope right there?
200. No, zero. Wait.
Okay, now this is day one. Wait, this is day one, but this is the foundation. If you lay a valid foundation for a house, things are going to happen over the next decade. Bad things. You get it?
100 in each rope,
Why?
because it's 200 distributed through 2 ropes.
Right. She's not going anywhere because there must be a net force of 0, right? There must be an upward force of 200 up. But
There's 200.
there are two strands holding her up. So what is 100 newtons up plus 100 newtons up?
200 units up.
That's 200 up.
Let's go.
200 up plus 200 down. Understand? Now I know why she's not going anywhere. The question now, just like Burl would ask, hey Hewitt, what would happen if she shifts and puts more of her weight on this ring? What do you think then?
Then that one would be 200 up and down.
If she puts all of her weight on that, if this rope goes kind of limp and there's no tension at all, then it would be 200 up, wouldn't it? But what if it's not? What if there's tension on both of them? Would you say that this one plus that one still has to equal 200 up?
Yeah.
So if that's 180, that would have to be 20. If that's 120, this has to be 80.
Yes.
And that's what he was talking about. He said at the time they didn't know the answer, but he figured out that's what it is. Now, do you understand how you can make mistakes because of things you've done in your past that made sense to you? This is something new. It's a little bit new way of thinking for some of you. All right, so questions about that. So the world of equilibrium, we already talked about that. You're either at rest or you're moving in a constant speed in a straight line, and in both cases, the net force on you has to be 0. Okay, let's go over here to the next page. Again, this is like an intro chapter. Matter of fact, this old book, before this new version came out, he simply meshed this one with chapter 3. And I used to have a test on chapter 3 and 4. The new book came out, and he separates this. Now we're having a chapter test on 2, 3, and 4. But it's really the same material. All right, let's read here. I need somebody to read down here, and then if everybody can see that. Everybody see that? All right, who would like to read today? Anybody? Can you see it or not? Would you be able to read it from back there? What do you think? Jeff, you want to read? Can you see that?
Yeah, I can read it.
Okay.
I can't.
Well, I mean, can you see it from back there?
Yeah.
Okay.
I was expecting that.
Consider a book lying at rest on the table as shown in figure 2.6a. The book is in equilibrium. What forces act on the book? One is the force due to gravity, weight of the book. Since the book is in equilibrium, there must be another force acting on it to produce a net force of 0. An upward force opposite to the force of gravity. Where is the upward force coming from? It is coming from the table that supports the book. We call this the support force. An upward force that balances the weight of an object on a surface. Support force is often called the normal force. For an object at rest on a horizontal surface, the support force must equal the object's weight. So in this case, the support force must equal the weight of the book. We say the upward support force is positive and the downward weight is negative. Two forces add mathematically to 0. So the net force on the book is 0. Another way to say the same thing is that.
The sum of all the forces equal. Sigma means sum of. Okay, go ahead.
To better understand that the table pushes up on the book, compare the case of compressing a spring shown in figure 2.6b. If you push the spring down, you can feel the spring pushing up on your hand. Similarly, the book lying on the table compresses atoms in the table, which behave like microscopic springs. The weight of the book squeezes downward on the atoms, and they squeeze upward on the book. The compressed atoms produce the support force.
Go ahead. One more.
When you step on a bathroom scale, two forces act on the scale as shown in figure 2.7. One force is the downward pull of gravity, your weight, and the other is the upward support force of the floor. These forces compress a mechanism, in effect a spring, that is calibrated to show your weight. So the scale shows the support force. When you're standing on a bathroom scale at rest, the support force, I can't see the rest of it,
And your weight. Okay.
and your weight have the same value.
Now they have the same magnitude, but they have opposite directions, don't they?
Yeah.
Everybody got that? Now, down here, you can't see this little blue box, but very much like the girl swinging on 2 rings. What if you had 2 bathroom scales at home? And let's say you weigh 160 pounds. You weigh 160 pounds, you stand on one bathroom scale, says 160. You stand on two bathroom scales evenly. What does each bathroom scale read?
Should read 80 each.
Well, I thought everybody would say that. I weigh 160 pounds. I'm standing on two bathroom scales. How much would each one read?
80.
80.
Oh.
Isn't that right? Now, the question though, just like Burl asked, and just like the girl on the rings, what would happen then? What if I were to shift my weight one way or the other? One number would start going up and one would go down. Question, would they still add up to 160 pounds?
Yes.
Yes.
Yes, they would, okay? You okay on that?
Yes.
This is a good start. You're doing a good job starting out the chapter. Now, let's go one more page, and then we'll, I may not be able to give you a handout sheet. I may wait till tomorrow and give it to you. Well, okay, let's go ahead. I need somebody to read this section here. Let me see if I can get that close enough so you can read it. All right, ready? Ready? You want to read?
Me?
Yeah. When an object isn't moving,
When an object isn't moving, it's in equilibrium. The forces on it add up to 0. But the state of rest is only one form of equilibrium. An object moving at constant speed in a straight line path is also in a state of equilibrium. Once in motion, if there is no net force to change the state of motion, it's in equilibrium. Equilibrium is a state of no change. A hockey puck sliding along slippery ice or a bowling ball going at a constant velocity. Velocity and equilibrium until either experiences a non-zero net force. Whether at rest or steadily moving in a straight line path, the sum of the forces on both is 0. Interestingly, an object under the influence of only one force cannot be in equilibrium. That force in that case is not 0.
Yeah.
Only when there is no force at all, or when two or more forces combine to 0, can an object be in equilibrium. We can test whether or not something is in equilibrium by by noting whether or not it undergoes changes in motion. Figure 2.8 shows a desk being pushed horizontally across a factory floor. If the desk moves steadily at a constant speed without change in its motion, it is in equilibrium. This tells us that more than one horizontal force acts on the desk. Likely the force of friction between the bottom of the desk and the floor. Yes, friction is a contact force between objects that slide or tend to slide against each other. More about friction in chapter 6. The fact that the net force on the desk equals 0 means that the force of friction must be equal in magnitude and opposite in direction to our pushing force.
okay, so I want you to think about that. Thank you very much. You did a good job for day one. If you want to keep on reading this, I will eventually assign some questions to you, but go ahead and read maybe the next 4 pages, and we'll get ready to start tomorrow. All right, thank you.